Good morning, everyone. So today we're going to go ahead and start with the gas laws. And so before we start the gas laws, I would like to talk about the 4 parameters that are always going to be involved into the gas laws. The first parameter is volume. And for volume, we use the letter V. So in the gas laws, whenever you see V, that's a volume. The second element involved in gas laws is pressure. We talked about pressure and its units and the conversions in a previous video. Pressure is labeled P. Then we have temperature, which is T, and it's always in Kelvin. For the volume, it's usually either in milliliters or in liters. So we'll get to the unit issue later. For pressure, as you know, it's either ATM, Dors, millimeter mercury, and again, we'll get to the unit later, or kPa. The fourth element that we always use in gas laws is the number of moles of gas. So number of moles of gas in question, of course. And the unit is MOL. Okay? So the first law we're going to cover today is Boyle's law. So Boyle's law studies the relationship between P and V, which means that the temperature, my apologies, I forgot to say something. MOL here, that's the unit, but the number of moles is N. So N and the unit is MOL. All right, let's get back to Boyle's law. So Boyle's law studies the relationship between pressure and volume, and therefore temperature and number of moles are constant. So we are not going to change these when we're studying the relationship between P and V. We keep them constant, okay? So when you have a given container with a piston here, piston means that it's allowed to move up and down. You have something like that, and so you have a certain pressure, okay, and you have a certain volume. So you have a certain pressure here and a certain volume here. Let's say now that you're going to do things a little bit differently, and let me just give myself a little bit more space here. So I'm going to move this down a little bit, and I'm going to draw another one. So it's the same container, but now I chose to move the piston up a little bit. So what did I do? So instead of having a certain pressure, now I have less pressure. So the pressure went down. What happened to the volume? It went up. Similarly, if I think about if I add the pressure on top of the container, the volume is going to go down. So it's an inverse relationship. So relationship between P and V is an inverse relationship. Have an inverse relationship. When one goes up, the other one goes down. Okay? So if I compare these two conditions here to each other, I can say that P1, V1, that's the pressure here and the volume here, is going to be equal to the pressure up here, which is the new pressure in the new volume. So the initial condition is equal to the final condition, even though P and V have different values. One has to go up and the other one has to go down in order to maintain the equality. Okay? So that's Boyle's law. That shows an inverse relationship. When P goes up, the V goes down. When V goes up, P goes down. All right, let me give you an example. So for example, if there is a 75-liter container with a volume of, no, sorry, there is a 75-liter container, that's already the volume, so I need to put the pressures with a 1.15 atm, and the pressure goes down to 0.86 atm. What will be the new volume? So here you look and you say, oh, I'm given a volume, I'm giving a pressure, another pressure, and I'm looking for the volume. So you're looking for, so you know that you're going to use something that has P1 V1 is equal to P2 V2. It's very important when we do the gas laws is to write your variables. Write everything that's given. You write down, what's P1? Well, in this case, P1 is, that's the first pressure given, 1.15 atm, which is associated with a certain volume. So V1 would be here in this case 75 liters. And again, it's very, very important to write down the variables the way I'm doing. It's going to make your life a lot easier. If the pressure goes down too, so those are the new conditions, so that corresponds to P2. How do I know it's pressure even if it doesn't tell me? Well, I know from the unit. You have to know that atm is a unit of pressure, that liter is a unit for volume. So my P2 is equal to 0.86 atm. And what's the new volume? Well, what's V2? That's what we're looking for. So we're going to be solving for it. So you write down the law, P1 V1 equals to P2 V2. You isolate the variable you're looking for. We're looking for V2. That's our unknown, right? So you have to remember how to isolate variables. So that means that you want to isolate the V2 and be alone on one side. So you need to get rid of the P2. So what do? You divide both sides by P2. So you get V2 equals to P1 V1 over P2. And the reason why I asked you to write the variables on the side like that, now it's very easy. You're just gonna plug in the numbers without even thinking. Why? Because you already know P1 is 1.15 atm, so we don't have to think twice. V1, oh, it's 75 liters. Instead of going back into the long paragraph and try to reanalyze it and figure out what's P1, what's P2, what's V1, it's a lot less hectic. So P2 is right there, 0.86 atm. And before you just plug in the numbers on the calculator, you have to always double check that your units make sense. So I have atm, cancel with atm, I'm left with liters, that's the unit for volume. Am I looking for volume? Yes, I am. So that means that I am on the right track. And then you take your calculator and you plug in your numbers. So I go 1.15 times 75 divided by 0.86. And I found 100.29. And since I have to stay with how many sig figs, you guys? Well, I have 2 here, I have 2 here, and I have 3 here. So my answer should have only 2 significant figures. So really what I'm going to do is my answer, instead of 100.3, that's what the calculator is giving me, and these are liters, it's really going to be 1.0 times 10 to the second liters. Okay? So you still follow the rules of significant figures, of scientific notation. So here, we're not going to do like with stoichiometry and start with the first number because we have 3 given numbers. So we go with the number that has the least amount of significant figures, just as you learned at the beginning of the year. So that's an example with Boyle's law. Next is Charles' law. Now with Charles' law, so let me draw a line here. So Charles' law. With Charles' law, you guys, we're studying the relationship between V and T, which means that the pressure in this case and that the number of moles are constant. So we're not touching this. We're only working under the same pressure, but we're playing with volume and temperature. So imagine that you have a balloon. So the balloon is not rigid, it's flexible. So you can make it bigger or smaller. Imagine that well, let's say you have a hot day and you blow a balloon, and then you take this balloon and you put it in the fridge and you come back later. What will happen to the volume of the balloon? It will shrink. It will go down. What happened to the temperature? It went down. So what happened to the volume? It went down. You take it back up outside, and what's going to happen? The temperature is going to go up, so the volume is going to go up. So the relationship, so Charles, a few centuries ago, he played with temperature and volume of gases, and he figured out that V1 over T1 is equal to V2 over T2. Which means that, this means that if I increase one, the other one's going to go up. If I decrease one, the other one's going to decrease. So it is a direct relationship. So there is between V and T, they have a direct relationship. Okay? So I can give you an example. Let's say it's a warm day, very, very warm. Oops. At 35 degrees Celsius, a balloon has 2.45 liter volume. Let's say has a volume of 2.45 liter. What will be the new volume if the temperature drops by 30 degrees Celsius? Oops. All right, a few things here. Number one, as we did with Boyle's law, we have to write all the variables. So what is my V1? Well, V1 is 2.45 liters. What's T1? Well, it's 35 degrees Celsius. But what did we say in the previous video about the temperatures with gas laws? You have to always use what unit? No exception. Always have to convert it to Kelvin, which means I need to add 273 to this. And that will give me the temperature in Kelvin. So 35 plus 273 is 308 Kelvin. And then V2 is what we're looking for, right? What will be the new volume? Yeah, so that's X, that's my unknown. And if the temperature drops by 30 degrees Celsius, so is the new temperature 30 degrees Celsius? No, it went down from 30 to 5 degrees Celsius. Why? Because it says dropped by 30 degrees. So it's really 5 degrees Celsius plus 273, that is 278. So you have to be very careful when you read these problems. All right, so now we're going to go ahead and solve for V2. So you write the equation. So V1 over T1 is equal to V2 over T2. Now, problem is, a lot of students mess this up, so please be careful. Mathematically speaking, this is the same thing as V1 T2 equals to V2 T1. And I hope you guys can see this. Because in math, A over B is equal to C over D. And you can rewrite it as AD equals to BC. Oops, sorry, this is a D. Okay, you guys? So that's the same idea, okay? What I'm doing here is the same as here, okay? So, and now you can isolate the variable. This is the best way to avoid making mistakes because a lot of the times the students will find the inverse of the new volume rather than the new volume, unless you are careful and you do it this way. This is the safest way not to make mistakes. All right, so again, I'm looking for V2, and therefore now I'm going to isolate V2, so I know to divide both sides by T1. V1 T2 over T1. And now that I have all the numbers, it's very easy to plug things in. Okay, so V1 is 2.45 liters. T2 is, oh, sorry, T1, no, wait, T2, yeah, 278 K divided by T1, which is 308. And you look at the units as we usually do, and the kelvins cancel out. I'm left with liters, which is the unit that I want because I'm looking for volume. Therefore, V2 is equal to, let me just get your calculator ready to do that. Your answer will have three significant figures, obviously, because all the numbers have three sig figs. 2.45 times 278 divided by 308. And that is 2.21 liters. I want you to notice a few things. Number one is that here it's a direct relationship, right? So because it's a direct relationship, the temperature went down. What happened to the volume? It also went down. The temperature went down from 308 Kelvin to 278, so it went down. The volume went from 245 to 221, so it makes sense. Let's double check that with Boyle's law. We haven't had the chance to do it. So you look here, between pressure and volume, it's an inverse relationship. So let's look at this. I had a pressure that went from 1.15 to 0.86, so the pressure went down. So the volume should go up. Did it go up? Yes, it went from 75 liters to 100 liters. So you know when you check these little tricks that you're on the right track. All right, a few more things. Another law, it's called Gay-Lussac's law. So this guy did study the relationship between P and T. So he kept the volume and number of moles constant. And what he found is, well, let's think about it. If you have a rigid container, which means that the container is not flexible, it's rigid, and you increase the temperature, what's going to happen? Well, the particles are going to have more energy. They're going to collide more often and with a higher force to the side of the container, which causes what to happen? It causes the pressure to go up. So as the temperature goes up, the pressure also goes up. So he found out that P1 over T1 is equal to P2 over T2. And he found that the relationship between P and T is direct. Have direct relationship. So again, as you increase the temperature of a rigid container, the particles will have more energy. They'll collide more often and with more force to the side of the container, which really means that the pressure will go up. So let's do another problem, a very simple problem. Let's say a container, a rigid container, it would be better to write it like that. A rigid container has 783 millimeter mercury of pressure and 311 K temperature. The pressure now let's do the temperature. The temperature is brought down. Consequently, the pressure goes down. Oh my God, I can't spell. Down to 699 millimeter mercury. What is the new temperature? All right, so as we usually do, what are we going to do? We're going to write down the variables. So I have my P1 is equal to 783 millimeter mercury. My temperature, my T1, is given in Kelvin, so hallelujah, I don't have to make any conversions. The temperature is brought down, consequently the pressure goes down to 699 millimeter mercury, so I have the P2 is given to me, and it's 699. Now, is it okay to keep the unit in millimeter mercury? Totally okay, because the millimeter mercury will cancel with the millimeter mercury. If you are given the pressure, one pressure in millimeter mercury and the other one in ATM, you have to convert one into the other. It doesn't matter if both are in ATM or both in millimeter mercury, but they have to be in the same unit, okay? Because the units are going to cancel eventually. And then T2 is my unknown temperature. And now I write my equation. I'm going to go ahead and write down P1 over T1 is equal to P2 over T2. I'm going to go ahead and isolate the variable, but be careful. I'm going to use P1 T2 is equal to P2 T1. The math we just did earlier up here, because it's very important to remember this. This is, again, the best way to avoid making mistakes, because if you realize here, my unknown is T2. And this is where the students most of the time give me the answer as 1 over T2, not T2. And of course, it's wrong. So the best way to avoid this mistake is to set it up the way we did here, okay? So please keep doing this. And then now I'm looking for T2, and T2 is going to be P2 T1 over P1. And so P2 is 699 millimeter mercury times T1, which is 311 Kelvin. And on the bottom, P1 is 783 millimeter mercury. Okay, so why is it that I don't care what unit it is in? As long as both of them have the same unit, the pressure, as long as the pressure is in the same unit, I'm good. It could be ATM, it could be millimeter mercury, it could be kPa, I don't care, or you can try it with all three different kinds of units, and you should find the same answer if you're doing things correctly. All right, so what are we left with? We're left with Kelvin, and that's what we're looking for. That's the unit for temperature. So what you do now is you simply plug in these numbers in the calculator. And again, I have 3 sig figs everywhere, so my answer will have 3 sig figs, and it has to be reported in scientific notation. So divided by 783, and I have 278 by rounding, 278 Kelvin. Let's see if this answer makes sense. The temperature went down. We know it's a direct relationship. If the temperature goes down, the pressure has to also go down, okay? So the pressure went from 783 to 699. The pressure went down, and the temperature also went down from 311 to 278. All right, so a famous question students ask me, how do I know which law to use? Well, look at what's given. When you set up your variables and you write them down, you'll figure out right away what law to use. If you're given a pressure and temperature before and after, pressure and temperature, that's going to be Gay-Lussac's law. If you're given a volume and temperature before and after, well, that's Charles' law. If you're given pressure and volume, it's Boyle's law. So it really depends on the data you guys are given. All right? Now, we have three different laws. We have P1 V1 equals P2 V2. We have we have V1 over T1 equals P2 over T2, and we have P1 over T1 equals to P2 over T2. So we have three different laws, okay? Can you guys see a way where we can combine all three laws in one law? Where do you see P? P is always on top. So I'm going to do P1. V is always also on top. Where's T? Always on the bottom. And this is going to be equal to P2 V2 over T2. We call this the combined gas law. And you see here that we have only the 3 out of the 4 parameters that are going to be changing. So in this case, N, the number of moles, is still constant. Okay, so we're not changing the number of moles here, but we can increase the pressure and see how the volume and temperature are going to react. I mean, it's complex. So I can give you an example of that. And after the example, you will see that I'll give you 4 worksheets. 1 worksheet on Boyle's law, 1 on Charles' law, 1 on Gay-Lussac's law, and 1 on the combined gas law. And I don't know if I have another one that will not tell you which law to use. You'll see. You'll read the directions on the worksheet, and you'll follow directions, and it shouldn't be too hard. But again, make sure to be consistent with pressure, that the pressure has always the same unit, and that the temperature is always in kelvins. Also, volume has to be in the same unit. I can't give you V1 in milliliters and give you the V2 in liters, for example. They both have to be either in liters or in milliliters, so be careful with that. All right, so let's say I have a container. So we're doing an example here. A container has 695 millimeter of mercury and pressure, 6.12 liters in volume at a temperature of 35 degrees Celsius. What will be its new temperature if the volume is 698 milliliters and pressure is 0.469 atm. You see what I'm doing here? Let's see. So I have a container so I have a P that is 695 millimeter mercury. I have a volume that is 6.12 liters and a temperature that is equal to 35 degrees Celsius, and right away you have to convert it to Celsius, right? To Kelvin. So 235, 273 plus 35, that is 308. What will be the new temperature? So I have a T1 and a T2. If the volume is now, so I have a V2, so this is a V1, and I have a new pressure, so the pressure here is P2, so this is P1. So T2 is, what is the new temperature? That's my unknown. V2 is 698 milliliters. Do you notice something? Well, I have liters on top and milliliters on the bottom. V1 is expressed in liters and V2 is expressed in milliliters. So I have to be consistent. So I'm going to choose to convert that into liters. And you should hopefully remember that in 1 liter, you have 1,000 milliliters. So basically, I'm going to have to divide that by 1,000. So it gives me 0.698 liters. Okay? All right. And then now I'm going to look at my pressure, which is 0.469 atm. Oops. This one is an atm. Up there it's in millimeter mercury, so I have to be consistent. What do I do? Well, you change one into the other. Well, I'm going to change that to millimeter mercury. I could have done the opposite, by the way. Nothing stops me from doing the opposite. I just chose that one. It just happens to. So I'm going to go ahead and do 0.469 times 760, and that is 356 millimeter mercury. So that's what I meant when I was talking about being consistent with the units. Okay, so now you have millimeter mercury here, you have millimeter mercury here, you have liters here, and you have liters here. Okay, all right. So now we can plug things in to solve for T2. Oops. So I'm going to go ahead and write on the equation. I'm going to do, oops, I need a blue color. So I go to P1 V1 over T2 is equal to P2 V2. Oops, what am I doing? This is a T1. And this is a T2 over here. Therefore, again, same idea. I'm going to just do the cross multiplication. So P1 V1 T2 is equal to P2 V2 T1. And therefore, T2 is going to be equal to, now you know you need to divide both sides by P1 V1, right? So it's going to be P2 V2 T1 over P1 V1. And now it makes it a lot easier when you have everything already here on the side, right? So you can just go ahead and plug things in. So T2 is equal to, so P2 is 356 millimeter mercury. V2 is 0.698 liters. And T1 is 308 Kelvin. And on the bottom, P1, 695 millimeter mercury. And V1 is 6.12 liters. And before you plug in the numbers on the calculator, you can look at the units. And you can see that millimeter mercury cancel out together. You can see that the liters cancel out together. And what we're left with is Kelvin, which is what we want because that's the unit for the temperature, okay? So now we're ready to plug in. We've verified the units, that they're done correctly, which means that we're probably on the right track. So now we do the math. So 356 times 0.698 times 308 divided by 695 divided by 6.12. And that is, calculator gives me 17.99 Kelvin. Whoa. That's a really low temperature. And that is really 18.0 Kelvin. Okay? Yeah, 3 sig figs. Yeah, all the numbers up here have 3 sig figs, so the answer will have 3 sig figs. Okay. If you guys have any questions, please make sure to write it down somewhere and let me know during office hour. All right, so just watch out. I'm going to post this I'm going to post some worksheets along with this lecture. And let me know again if you have questions. It would be a great idea is you watch, you take a piece of paper, or sorry, not a piece of paper, old school, sorry, but you take notes on your iPad, whatever it is, and bring it up to me when we have office hour. And before I go, I just have to apologize because I'm sure that you heard my parrot long enough in the background. But yeah, he's happy. He's a happy camper. So anyways, all right. Talk to you soon.